Uh, Hi, today we discuss this some of the sequential intricacies. One of them is, let's see, well, the tail of the sequence. Consider consider a sequence an. Mm, you see the sequence an. If we expand this a1, a2, a3, and so on, you will get the general term, any arbitrary term an, and then it continues to the infinity. So now we define the tail of a sequence. Tail of a sequence. So what does this mean? See here, remove any finite number of terms from the sequence. First finite number of terms. Let us say they remove the terms from a1 to an, then the remaining sequence is called the tail of a sequence. That means the terms from an plus 1, an plus 2, and so on, the remaining the sequence is called the tail of a sequence. Okay, so whenever, what does this here we can choose n as large as we want. The tail contains the remaining infinite number of terms of the sequence. All types of sequence were discussed so far are just analysis of the tail of the sequence. If a sequence is convergent, if this sequence is convergent, then its tail is convergent. If a sequence is monotonic, then its tail is also monotonic. If a sequence is divergent, then its tail is also divergent. Okay, so it plays some of the important role in the behavior of the sequence. For suppose, for example, take a sequence 1 2 5 3 7 4 6 5 10 1 2 3 4 5 and so on. Okay, here you can see the sequence here 1 2 3 4 5 6 7 8 9. Okay, up to 9 terms, the sequence is random. From the 10th term, the sequence is monotonically increasing sequence. So the tail of the sequence is monotonically increasing. So whatever the behavior of the sequence, see, we can okay, see here, the tail is monotonically increasing or monotonic sequence. Such sequences are called monotone after finite number of terms. Monotone after finite number of terms. Okay, we can apply the monotone convergence theorem. for this monotone after finite number of terms whose tail is monotone. Okay, and what is the monotone convergence theorem? It says that any bounded a sequence which is bounded and monotonic implies that it is convergent. Okay, a bounded monotonic sequence is convergent. So if in case of here, that means instead of the monotone we can use the whose tail is monotone, whose tail is monotone. Okay, so such sequences a bounded plus tail is monotone implies the sequence is convergent. Bounded monotone sequences are convergent. Okay, so we can, this is the terminology. Instead of strictly monotonic we can use whose tail is monotone. Even that sequence which is bounded is convergent. Okay, first now we see that is this now we say this is the converse is true. Converse of this theorem, is it true? We will see that the question, if a sequence is convergent, if a sequence is convergent, then is it bounded? Is it monotonic? Is it monotonic? Is it bounded? So we examine these two properties. If a sequence is convergent, then we will check whether this is monotonic or whether it can be bounded or not. So we have two possibilities here. So first we check one condition, that is it monotonic or not. So convergent sequence implies the monotonic or not. This is the question. So we will take, I know this is the false, this is not true, and so I try to prove this by the counter example. I will take a convergent sequence and which is not monotonic. So then we can conclude that every convergent sequence need not be monotonic. So let's take example. First example is minus 1 by 1 and 1 by 2, minus 1 by 3 1 by 4 minus 1 by 5 and so on. So see this is the sequence whose nth term is finding that whose nth term is like this, minus 1 whole to the power of n. So if we take limit n tends to the infinity, this is going to, so if n tends to infinity, the numerator will be either plus 1 or minus 1, but in the denominator it gets to the infinity, so the entire an term is tending to 0 as n tends to the infinity. So the sequence is converges to the 0, then is it monotonic? As you can see that see, this is the negative, so from here to here it is increased, so this is positive 1, half is positive, from half to the negative, from here to here it is decreased, from this to this it is again increased and decreased, so it is not monotonic, and this continues as long, this continues throughout the sequence, so the above sequence is not monotonic. So we can conclude that a convergent sequence need not be monotonic. Convergent sequence does not imply that a monotonic sequence. What do we have another condition, the convergent implies the monotonic bounded or not. Convergent implies bounded. Next question is that one. Convergent implies the boundedness or not. So to explain this one, let's take I will use the help of the graph of the sequence. For suppose we have a sequence which is convergent, let's say or suppose this is 2, a sequence is converging to the 2. I will take very simple example of monotonically decreasing convergent sequence. Okay, for suppose if it is 100 and this is 1, 100th term of the sequence is here. So if we consider this one, consider such sequence, let's see that the an, this sequence is considered, this sequence is an denoted with the an, and this is 100th term, a100. See, a100, the difference between the 2 and the a100, let's consider it is very small, and it is getting smaller and smaller as the n increases from 100 and from 100. So for suppose if this difference is 1, let us consider that a100 is 3, then a101 is, it is still decreasing, right, is less than 3, that is a100. So you can, since it is monotonically decreasing, you can create the chain of the like a100 which is greater than a101, which is greater than a102, is greater than a1 or 3, which creates a chain of the sequence, right? So all of the remaining terms, since the sequence is converging to 2, that we have each and every term of this sequence must be greater than or equal to 2. Since it is monotonically decreasing and grazes to the 2, it never crosses the line of the 2. Okay, so that thing is possible. So 100 is 3. See the tail of the sequence here. The tail of the sequence 100. See the here. This is called tail. See here. Tail is bounded. Tail is bounded. So then the sequence is bounded. Okay. How we can say that is, see this, see here, from 100 to up to a infinity, all of the terms is bounded between 2 and 3, right? So choose a maximum and minimum from a1, a2 and so on a99. Okay, we can choose which is maximum 1 and minimum 1 from this finite set. Okay, so this an is in between the maximum 1 and the minimum 1. Okay, so now where n is from 1 to 99, you can see this here. If n is 100 to infinity, it is bounded between 2 and 3. Okay, so here see, even this is having bounds and this is having bounds. We can choose which is maximum here. Okay, among 3, see here, among 3 and the maximum number among this set, among 3 and the max, we can choose which is maximum. Okay, that maximum we can write. Among the minimum and the 2, we can choose which is minimum, and we can take this works for all n. Okay, we choose the minimum of the minimum and the maximum of the maximum. So this max and this minimum works for all n. So in general it works for all n, where this is constrained from 1 to 99, this is constrained from 100 to infinity. Okay, so the now we shown this sequence is bounded. Now we shown that this is bounded, right? Okay, so with this we can conclude that a convergent sequence is bounded. Every convergent sequence is a bounded sequence. Okay, we took an arbitrary sequence, okay, and we shown that is bounded. So every convergent sequence is bounded, but every convergent sequence need not be the monotonic. Okay, but every sequence which is bounded and whose tail is monotonic is convergent. Okay, that's what happens. So next we go to the recursive relation of the sequences. Recursive relation. So what does this say? Recursive relation. So we know what is recursive means. It is completing itself and generates another one using the same relation, right? So this is extensively this is used in the sequence in sequences also by determining how the sequences behaves. That means we give a condition to the sequence. Let us let me explain with an example there. For suppose consider a sequence like a1, a2, a3 and so on. We have an minus 1, an plus 1 and so on. Now if we define a general relation an is equals to an minus 1 plus 2, I define a general relation like this. So see here, there are two ways to think how does this relation works. One way is an is dependent on its previous term. An minus 1. Okay, so an is dependent on its previous term, an minus 1. So similarly an minus 1 depends on its previous term an minus 2. So if you want to get the an, you need to know an minus 1 and then add 2 to that, then you will get the an. The second thing is, how do we think if you want to write if you want to find an minus 1. See here we consider, here it is n, then n less than 1. So what do we do here is n minus 1 plus 2. So without understanding anything, you can go through using the relation given there. So what you will get is an minus 2 plus 2. Okay, if this relation is continuous, so what we will know is a3 is dependent on a2, like a3 is equals to a2 plus 2. a2 depends on a1, a2 depends on a1, we add the 2. So what is this? Then a1 we don't know. So normally what they do is they used to define the first term. See here, an is dependent on its previous term, only one previous term, so they would define a1. Okay, so usually here they give a1 is 0 or something. They can give 0, 1, 2, 3, whatever the number they use, they can give, and then we can add 2 to that to get the continuous sequences. So in this particular example, a1 is 0, a2 is, we add 2 to the 0, 2, 4, 6, 8 and so on. It goes like that, all the even numbers. For suppose if, so see this, we have a relation here, we have a relation and one term is specified. So here this a1 is not compulsory that you need to specify a1, but intermediate, okay, any one term is given in between any one term is defined, then we can able to obtain the next three subsequent terms and its previous terms also. So, but generally they will define the first terms a1. Here this relation is so simple, this recursive relation is so simple, but we will have some more complicated relations also. So an is an minus 1 plus an minus 2. See here, an is defined using the previous two terms. So an is dependent on, now here an minus 1, an minus 2. Here an is dependent on define. So here an is depends on an and an minus 2, an minus 1 and an minus 2. So an depends on its two previous terms. So if we continue this, a3 is dependent on its two previous terms, a2 and a1. Okay, so if you continue this, a3 is dependent on its two previous terms, a1 and a2. So now you can see this, a2 is dependent on, must be dependent on its two previous terms, a1, and there is no other previous term. So we must define a1 and a2 here. At least two terms must be defined, two subsequent terms in the sequence must be defined. So then what will we get? Then we can define the entire sequence if we do the a1 and a2. Okay, so see, this is an example of the recursive relation. How does it behave and what is its point to generate the sequences. Okay, so there are some more complicated recursive relation to generate a sequence, but in the problems they ask not only to find the sequence, but they ask us to check whether it is convergent, bounded, or monotonic, some of the properties of that sequence. They want us to check that. So with the recursive relation, it doesn't end here. Okay, is it new that this is the recursive relation that we are learning? Is it new concept? Is it new concept? So we generate, we know how to find the general term an, right? We know how to find the general term an. So for suppose an is minus 1 to the power of n by n. Okay, in some of the sequences, so in this it won't work. Okay, let's take another example. An is, let's say, 4 to the power of n by n factorial. This is the general term of the sequence. So in such sequence, an minus 1 is 4 to the power of n minus 1 by n minus 1 factorial. So the an we define as 4 by n into 4 to the power of n minus 1 by n minus 1 factorial. So 4 by n a to the power of n minus 1. So here, see this an is generated using its previous term an minus 1. So this general term gives the recursive relation. This general term gives the recursive relation to generate the sequence. Okay, and here you no need to specify the first term of the sequence. A1 is 4 to the power of 1 by, we know that, in factorial. So this is what we say that it is generator. So some of the nth term generate from that. If we define the nth term of a sequence, from that we can obtain the recursive relation. If we use the recursive relation, sometimes we can have the nth term also. Okay, this concept is not new to us, but let us solve some of the problems here in as explained. So let us solve only this one. So let's take the above sequence which is defined above. So an the sequence an is 4 to the power of n by n factorial. Okay, so let us consider the sequence. If we use the sequence here, let us find whether it is monotonic or not first. Okay, let's see. We can use the question is like this. Show the sequence an is convergent. I use CGT for the convergent using monotone bounded theorem, monotone convergence theorem, using monotone convergence theorem. Using this theorem, we need to show that the sequence is convergent. So first we will show that it is monotonic, and then we will show that it is bounded, then which implies that the sequence is convergent. If possible, we will try to find what is the limit of that sequence. Okay, so for suppose here, let's take what is the first step. The first term of a sequence is 4 by 1 factorial. Second term of the sequence is 4 square by 2 factorial, 4 cube by 3 factorial, 4 to the power of 4 by 4 factorial, 4 to the power of 5 by 5 factorial, 4 to the power of 6 by 6 factorial, and so on. So we have something like this. So this is nothing but 4. This is 4 square. 16 by 2 is nothing but 8. See here. So this is nothing but 4 square by 2 factorial. This is can be written as 4 square by 2 factorial into 4 by 3. Okay, this is nothing but 8. So we can have this is 4 by 3. So similarly, this is also written as 8 into 4 by 3 into 4 by 4. 4 by 4 is nothing but 1. So this can be written as 8 into 4 by 3 into 4 by 4, that is 1. This time its previous term into 4 by 5. So this one can be written as 8 into 4 by 3 into 4 by 5 into 4 by 6. Okay. Say this here. So we must know that first suppose a number a is multiplied by a number which is greater than 1, like 1.06. The resultant number what we get must be greater than a. Similarly, a number a is multiplied by a lesser number like 0.9. It must, the resultant number here must be less than the original number a itself. See here, 4 by 5 is less than 1. So this must be, so the resultant number must be less than its 8 into 4 by 3. So this is 8 into 4 by less than its previous term. This is a4. And then look at here. So this is a5. a5 into any, see this is 4 by 6 is a number which is less than 1. So if I multiply that, the resultant is a6. The resultant number is less than a5 itself. So this is a6. a6 is less than a5. So when you look at the when we take a look at the terms, so a1 which is less than a2 is less than a3 is less than a4, which is greater than a5, which is greater than a6, which is greater than a7, which is greater than a6, and so on it goes. Okay, and we can prove this. From a4 onwards, the sequence, the tail of the sequence is monotonically increasing. Okay, so we don't need to bother about how to prove that thing. So is it bounded? Yes. Is it bounded? Yes. A1, A2, A3, A4, which is greater than A5, which is greater than A6, A7, and so on. See here, this is 4, 8, 8 into 4 by 3, this is 8 into 4 by 3, and so on. So, see here, is it bounded? So each and every term, so an is 4 to the power of n by n factorial. See, the term each an is always greater than 0. Okay, always greater than 0. Since it is positive, each and every term is positive, so we can say that it is greater than 0. So the tail of a sequence which is monotonically decreasing is bounded below by the 0. So a monotonically decreasing sequence is bounded below is convergent. Consider. So this is one type of so the monotonically decreasing sequence, which is bound below is convergent. So this is the application of the monotone convergence theorem. So we concluded that this is convergent. So now we examine whether what does it converges to. What does it converges to? Four to the power of n by n factorial. That we take the limit n tends to infinity 4 to the power of n by n factorial. Okay. For suppose limit n tends to infinity a n is convergence to L. Okay. Similarly, we can say that limit n tends to infinity a n minus 1 is converges to L also. Right. We are taking the previous term. That's it. So that a n we can say that here it is 4 by n into a n minus 1. Limit n tends to infinity. I take the limit on both sides. Limit n tends to infinity 4 by n into a n minus 1. So we take both the limits here. Limit n tends to infinity. We know that this limit is also exists. We consider, let's say this one. Then that implies the above statement implies this one is also L. 4 by n, the limit n tends to infinity a n minus 1. See here, this is nothing but L. 4 by n is nothing but 0 into L. So this is 0. So L is nothing but 0. So limit n tends to infinity. So this one is nothing but 0. Okay, that's how we can find the limit of the sequence. Next, using the recursive relation itself, let us solve some more examples. Using the recursive relation. For example, we have a n plus 1 is equals to minus a n and a1 is 1. So from here we can define that see here a2, see a n plus 1 is depends on its previous term a n. If you get the negative of a n, you can get just n plus 1. So a2 is nothing but negative of a1, that is minus 1. a3 is negative of a2, that is minus of minus 1 is plus 1, that is negative of a2. a4 is negative of a3, so we have minus 1. So this sequence goes like this: 1, minus 1, 1, minus 1, minus 1. So the sequence is an oscillating sequence. Okay. So let's take another example of that recursive relation. A n plus 1 is 2 into a n. So a n plus 1 depends on a n. So if we multiply the a n with the 2, then you will get an plus 1. So here a1 is given as 2. So a2 is 2 into its previous term a1. So 2 into 2, that is 2 square. Similarly a3 is 2 into its previous term a2. So 2 into 2 square, that is 2 cube. So if you continue like this, n is nothing but 2 to the power of n. So this sequence diverges to infinity as n tends to infinity. Similarly, we can have another relation. An plus 1 is nothing but n plus 1 into an for all n, where a1 is given as 1. Now we define this. a2 is nothing but see here, n plus 1 is multiply same n plus 1 here, so 2 into a1. So we have 2 into 1, that is 2. Similarly a3 is we multiply with the 3, a2 is multiplied with the 3, so 3 into 2, you can write this as 3 factorial, this is as 2 factorial. Similarly a4 is 4 is multiplied with a3, so we get 4 factorial. So if it goes, an is nothing but n factorial, which tends to infinity as n tends to infinity. Okay, so this is how the sequence goes. The recursive relation of the sequences. Now we take some other examples like using squeeze theorems. Let us take an example using the squeeze theorem. So solve and find the limits of the sequences. The limits of the sequences using squeeze theorem. Okay, first example 1. Find the limit of the sequence sin n by n. Okay, so using the squeeze theorem, they mentioned that you need to use this theorem there. How do we use the theorem? What is the squeeze theorem? Squeeze theorem mentions that if an is less than or equals to bn is less than or equals to cn are three sequences whose n terms are in this relation, an converges to the l, cn is also converges to the same limit l, then bn also converges to the same limit, then bn also converges to the same limit. That's what it says. So sin n, this we know is in between -1 and 1. So sin n by n is in between n by n and -1 by n. So we know as n tends to infinity, this converges to the 0, this is also converges to the 0, so this must converge to the 0. So we know limit n tends to infinity sin n by n must be 0. This is also true for the cos n by n. Limit n tends to infinity cos n by n is also 0. Okay. Same goes with it. So we can have another sequence. For example, 2n minus sin n by n, the frequency. We need to find the limit for that. So if we take limit n tends to infinity 2n minus sin n by n, see here we can divide this as 2n by n minus sin n by n. So this is nothing but 2 minus sin n by n. See, we use the squeeze theorem. From here we use the squeeze theorem that we know that it is converges to the 0. So 2 minus 0 is 2 as n tends to infinity. That's it. We'll solve some more. Okay. In the next video I will upload that what are the different types of different problems in the squeeze theorem, and some of the general finding the limit of the sequence. Okay, we'll solve few more, only must be 4 or 5 problems. So we stop here.